Bryan is essentially the chief software architect for DE4000, ACM 4000, and a range of other products here that are released or are about to be released. So Bryan is obviously a great resource here and a very knowledgeable resource on the operation of the D4000 configuration and so on. So Bryan has graciously given his time here this afternoon for us all here to get up to speed on current state of the D4000 and in particular the advanced scripting. So Bryan, thank you again for joining this afternoon here, sir, and I will turn the floor over to you.
Thank you, Dave. It's a pleasure to be with all of you this afternoon. And as was mentioned, we have a lot of exciting things coming up with not only the DE4000, but other products like the ACM 4000, which will integrate very closely with the DE4000 and enhance a lot of our communication capabilities with the DE4000 and with additional products, whether it be our the legacy Altronic products, new Altronic products, or even third-party products. A big part of that is being able to interface through Modbus and other communication protocols such as CAN J1939, be able to bring in all of that data and produce it and display it in a unified manner. So we may cover some of that a little bit more later in the session, but what I wanted to do today, something we haven't done in quite a while, but I'm going to apologize in advance. I'm going to cover a wide range from very simple to more advanced in terms of scripting with the DE4000 and our Lua scripting environment. So this may be old hat for some of you. It may be new for some of you. And so I'll try and take a very gradual approach, starting at the basics and working up to some of the more advanced scripting concepts with the DE4000. Feel free to interrupt and ask questions as we go along. That might be easier than keeping them to the end when they may not make as much sense or may be difficult to get back to. So we'll try to make this interactive if you've got questions or comments as we go. And with that being said, I'm going to start sharing my screen. And so I wanted to just give a little bit of background on the Lua programming language. It's been around for quite a while. It was first created in 1993 by some individuals at the Pontifical Catholic University in Rio de Janeiro, Brazil. And it might seem, anyway, there may be questions about, why this language was created back then and how it's become so popular. The environment at the time was such that it was very expensive to import computer hardware or software into Brazil from anywhere else in the world. So it's not like today where everything was open source and freely available. So when they needed a programming language, they weren't able to just go out and purchase one that was already in existence. So they created one of their own, and that's how Lua came about. Lua has become very popular as of late with with the internet and with online gaming. It's such a flexible programming language that it's embedded into games such as World of Warcraft and other popular video games, where players can write their own scripts to create their own characters or create their own user environment, or even create new game levels and so on. But it's used in many other applications as well, especially embedded electronics, and that's why we selected Lua for our uses. And as many of you know, it's been very helpful to have this programming environment, and it's really extended what we've been able to do with the control systems of the DE4000, and it's enabled things like yard valve control and advanced control strategies based on oftentimes 2 or 3 different control inputs, and being able to set priorities between them and react dynamically to changing conditions. But also we've been able to expose the programming environment to the user, whether that be our distributors, our customers, or our own internal engineers. And that's allowed us to develop custom applications quickly and adapt those applications, sometimes right in the field or on very short notice. And we've had a number of individuals who have been kind of self-starters and have really jumped in and learned the language. So it's something that we can provide as a service, definitely if needed, but it's also something that anyone can pick up and learn themselves. And so I want to get into that a little bit today. The best resource for anyone that's interested in Lua is their website, lua.org, and you'll find all the information there about the language itself. Now, we've built functions and other things on top of the Lua language, and we'll get into that a little bit later on in this session. But what I want to do is just start with the actual Lua language itself and show a little bit about how it works. And then I think it will make more sense as we then get into some of the custom functions that we have added on top of Lua. And you'll see how they just take advantage of the the actual built-in Lua capabilities, but just extend that and expand that. So a really nice part of this lua.org website, if you go to this Get Started page, and then under Installing here, click on this link for the live demo. It brings up a window where you can actually write Lua script and run it. So you type your script in the box here, and then you click the Run button. And I'm going to just give a few examples just so you can see how that works. So you can declare a variable just by giving it a name and the equal sign and then some value. So it could be a numerical value, a equals 1. And then there's a print function that you can put a variable within parentheses and print that variable. So if I just say a equals 1 and print a and run that, you'll see the output says 1. I can create multiple variables, and then I can do calculations with those variables. So I can say b equals 2, and I can say c equals a plus b, and I can say d equals a times b. And then I can print, oops. When I run this, it'll print the values of A, B, C, and D. And so that's just simple math functions, addition and subtraction. In addition to numerical values, we can also do string values. So I can say name equals Bryan. And you have to surround a string within quotes. And that's helpful to the language, because if you say name equals 1, it's going to treat it as a number. But if you say name equals quote 1, then it's going to treat it as a string or text. So strings or text are always in quotes. So I can say name equals Bryan. Well, let's say first name. Let's say last name equals Worth. And then if I try to say full name equals first name plus last name, if I would try and run that, you'll see it gives me an error. So I can't use addition in Lua with strings. Some languages allow you to do that. But in Lua, the plus sign is only meant for adding numbers together. So if you want to add or concatenate two strings, the operator for that is just 2 periods. So if I say full name equals first name dot dot last name, and then print full name, you'll see it prints Bryan Worth, but it's run together. So what I can do is I can say dot dot and then a space, which is also in the quotes, and then another dot dot to add that. So now I've got first name space last name, and if I run that, it'll say Bryan Worth. So that's how we add and concatenate numerical values, string values, etc. Numbers can be floating point numbers. In other words, they can have decimal values. They don't have to be just whole numbers. And Lua treats those internally just as numbers, whether they're a whole number or a fractional number, and can do full math functions on those as well. So I can declare A and B as floating values and C as A times B, and it'll print that value. There are looping functions such as a for loop, and these are common in pretty much any language. But it's very easy to set up a for loop. Let's say we want it to run 10 times. And so we can declare a variable I, which is going to cover the range of 1 to 10 every time we go through the loop. And so I say for I equals 1 to 10 do, then I can say print the value of I is. And so each time we go through the loop, it's going to add this string, the value of I is, with the actual value, and print that. And so you can see it's stepped through that. We can also do conditionals, things like if statements. So I can say if I is less than 5, then
Did we lose Bryan?
Can you hear me?
We can now, yes.
Okay. So when I run this loop, it runs 10 times, but every time I is less than 5, it prints 1 is less than 5, 4 is less than 5, etc. But it doesn't print anything if it's greater than 5. So I could do another if statement. Now we have 1 is less than 5, 6 is greater than 5, and so on. And I could put a third one in there for equals. Okay, so now I've covered all my cases: less than 5, equal to 5, greater than 5. So that just shows, looping constructs like the for loop, as well as conditionals like the if. We can shorten this up a little bit and use an else if. So we can say if I is less than 5, print that, else if I equals 5, then we print equal, and then the only other possibility is I is greater than 5, so then we just say else, and that covers all the other cases. And we see we get the same output, it's just a little bit condensed. So now that's all pretty straightforward, but I want to give you an example of how we expand Lua by creating additional functions. And so I'm going to show you how you can actually create your own function. So we're going to create a function called getChannelValue. And you can think of this in terms of the DE4000. It's going to accept 2 parameters. One is the terminal number and one is the channel number. And the function definition starts with function, and then the name of the function, and then the parameters in parentheses, and then ends with the end statement. And so I'm going to get rid of my for loop here, and I'm just going to call that, sorry, I'm just going to call this function. And inside the function, we have to return some kind of a value. So I'm just going to return 100. Call this CV for channel value. Okay, so I ran this function. I passed it a terminal number and a channel number, terminal 1, channel 1, and it just returned a value of 100. But it's really not using those terminal and channel numbers. So let's use those. And so let's say return value equals 32 plus term minus 1 plus chan. So what this is going to do, if terminal number is 1, it's going to subtract 1 from that and make that 0, and this should be times. So for terminal 1, the value returned is just going to equal the channel number. So if we put this on a loop, and just pass 1, chan for the channel number. Okay. Oh, we need to return this return value here. There we go. Okay. So this is returning the channel number as the channel value. And then we can actually put a loop inside of a loop. So we can say for term equals 1 to 2. And then we can pass term in instead of 1. So it'll run terminal 1 channels 1 to 32, and then terminal 2 channels 1 to 32. And it's helpful when telling you when you make a mistake. Okay, so we can see here after we get to channel 32, it just continues on, and it would be helpful if we show the terminal. Here. There we go. Now we can see the terminal number and the channel number plus the return value. So so we've written a number of functions such as this get channel value, and we actually have this exact function available on the DE4000. But instead of doing what I'm doing here just to create a fake return value, it actually goes out and reads that analog input on terminal 1, channel 1, for example, and gives you back that value that you can then use in your scripting. So let's get out of this Lua demo page here, and let's actually move back to the DE4000 and start writing some actual scripts. So if we go to global, go to scripts, and then if we click on the master script, the master script is a Lua script, just like the ones we were just writing on the other page there. This script is executed about 4 times per second, and so it's just constantly running in the background. So anything you add in this master script is going to run all the time, regardless of whether the if it's a compressor engine application, whether the engine's running or not, what the running state. We have our state machine with states 0 through 10, and regardless of the state, this master script's just always going to run. And so this is the place for scripts that you want to pretty much have running all of the time. And there's other places where we can put scripts where they only run certain times, and we'll show that as well. But if I click the master script button, then it brings me up into an editor, and I can do just like before: A equals 1, B equals 2. But I really can't do a print because there's really nowhere for that print command to show up. But what I can do is I can set a virtual channel. So it's a status, what we call a status variable, and that's what the S in svert stands for. but it's not a true channel. It's a virtual channel. So so that's why the command is set svert. And so we can create any virtual channel that we want. And so I can just call one called script output, and I can put whatever I want here. So I could say C equals A plus B, and I can set script output to C. And if I save that, it's going to start running immediately, and it's going to set this virtual channel called script output. So I'm going to go ahead and save that. So now if I go to my dashboard and add a dashboard element and filter down to my virtual channels, I should see that script output. And there it is. Script output 2.0. Oh, I should have done A plus B. There we go. Okay, so my script output is 3. Virtual channels are not limited to numbers. They can be text as well. So if I go back to my script here, I can say C equals again, I use the double dots to add the string C equals with the actual variable of C. And so there's my output there. So let's get into something a little bit more interesting. What I'm going to do in this case, I'm going to create a variable and when the script first runs, this variable will not exist, so we want to give it an initial value. So the easiest way to do that is to say, so my variable is called counter, and I want to give it an initial value of 0. So if I say if not counter, then counter equals 0. So this little chunk of script here is really only going to run the first time, because the first time this statement is true, counter does not exist or does not have a value. And so it creates it and gives it a value of 0. Every other time this script runs, it's going to jump over that because counter does have a value. So what I can do down here is I can increment counter to say counter equals its current value plus 1. And then I can set that to my virtual channel script output. And now I have a counter. It just takes a second for the script to load, but once it loads fully, then you should see the counter value start to increment. There it goes. So, so let's do something with actual channel values. So if I go back, if I go to my channels, you can see I have a channel on terminal 1, input 1 set as suction pressure, and it currently has a value around 118. So if I go back to my script, I don't need the counter anymore. So I can just say, I'm going to use SP for suction pressure and just say SP equals get channel value. And this is the same function that we created a little bit ago, but in this case, I'm going to do 1 for terminal 1 and 1 for channel 1. And Let's say suction pressure. And give it a value of SP. No, it's making that too long because of all the decimal points. Just a moment here. So there's a math function called floor that basically truncates the fractional part off. So there you see my suction pressure is 118. So let's do something a little bit more useful. So let's create a differential pressure between our suction and our discharge. So if we go to channels, we see that terminal 1, input 1 is suction pressure, and terminal 1, input 2 is discharge pressure. And so if we make our discharge pressure higher than our suction pressure, then we should be able to calculate the differential between the two of those. So we're going to say suction pressure is get channel value 1,1, and discharge pressure is get channel value 1,2. And instead of using this virtual channel called script output, I'm going to just call this differential pressure. And I'm just going to put the numerical value in there. So I'm going to say diff equals dP, which is my discharge pressure, minus SP, which is my suction pressure. And then I'm also going to say if dP is less than 0, then dP equals 0, just so that our differential pressure can go as low as 0, but never goes negative. And so I'm going to set this virtual channel called diff press to diff. And so now if I go back to my dashboard, I can delete this virtual channel and add the one we just created called differential pressure. And let's add the suction and the discharge so we can see those as well. So we'll do the suction pressure as a radial. And over here, we'll do the discharge pressure as a radial. All right, so we can see when our discharge pressures 423, suction pressure is 118, our differentials 305. So now we have something that's useful because it's different than the normal values that are part of the DE 4000. It's a calculated or a virtual channel, but we can use this in a number of different areas. So let's go to our startup sequence. And so I've set all these times basically to 0, so we don't waste a lot of time going through these steps. But in the warm-up, we can create a condition or a permissive. So let's say that we don't want to get out of the warm-up state until let's see if this is the right. I think I named it differently than, yeah. So it's this channel differential pressure. Let's say we don't want to get out of that warm-up state until our differential pressure is greater than 200. So we'll go ahead and save that. And we'll go back to the dashboard and we'll make sure that we're starting with a differential pressure less than 200. And so you'll see if I start up, we'll step through the states quickly, and then we'll stop at the warm-up state. And that differential is causing it that permissive is causing it to stay in that warm-up state until that differential pressure exceeds 200. So I'm going to go ahead and increase that. And you can see as soon as we exceeded 200, then it went on. So so going back, just to review what we did there with our startup states. Each startup state can have up to 2 built-in permissives, but we can also create an unlimited number of permissives in scripting, or permissives that combine 2 or 3 or 4 different values and does some kind of computation or logic on those multiple values. So if you've already set up 2 permissives, but you say, oh, I need to look at something else as well, you can combine those 2 into a single virtual channel, or even take those 2 plus another one, and create a virtual channel and set it up as we did here as a permissive. So let's look then at how we could use that differential channel to do something like valve control. So let's go to outputs. And what I want to do is I want to create an output. Let's say this is for a bypass valve. And let's say we want to protect the compressor by not allowing the differential pressure to get above 500. And so we want our logic to say if the differential pressure is greater than 500, then we're going to open this bypass valve. Otherwise, we're going to leave it closed. But let's also say that we are going to leave the bypass valve open when we're going through our startup states. But then once we get to the warm-up and our differential pressure exceeds 200, then we're going to close the valve. So really, when we're in state number 8, that's when we want to test that differential pressure, and if it ever gets above 500, then we open this bypass valve. So we want to select an output, so we can select terminal 1, discrete output 1, and we're going to say that when that valve is energized, it's open, and we want the state 0 position to be open. So we always start with the bypass open, and then what we want to do then is in state 8, instead of setting that open or closed, we want to just create a script. And so you see in state 0, the condition is open. States 1 through 7, the dot means it's just the same as the previous value. So in all of those states, it's open as well. And then in here, we want to say if so we want to use the get svert. And So one thing I want to explain about this get svert function, depending on the order of how things execute, this script may run before you've actually created this virtual channel called differential pressure. So this additional parameter here that I have set at (0), that allows you to assign a default value if that virtual channel does not exist. But as soon as it's been created and has a value, then it will return that value. So I'm saying if this differential pressure is greater than 500, then we want to return closed for the condition of that valve. Otherwise, we want to return open. So I'm going to save that, go back to my dashboard, and now I want to add an element for that bypass and set that as a valve so it either shows open or closed. And I'm going to reset. I'm going to turn my pressure down so we haven't met that permissive yet. Go ahead and get started. So it's waiting on the permissive. So let me go above 200 on the differential. And our bypass valve I think I've got the wrong return value in there. Just a second.
Folks, do we lose Bryan?
I'm here. I'm just looking something up real quick. Sorry.
Okay, no worries. Just wanted to make sure we didn't drop you off.
Yeah. Can see him typing.
Okay, I've got my logic backwards. That's it. Okay, so if the differential pressure is greater than 500, then we want the valve to be open. Otherwise, we want it to be closed. So we either just return a string that says open, or we return a string that says closed. And so now you can see when the differential pressure is above 500, the bypass is open. When it gets below 500, then the bypass is closed. And then as soon as we stop, we go back to state 0, which again on our output control, state 0 is open, and all of the other states up to state 7 are also open. So if we run through that startup process again, we'll see that it will stay open until we reach the running state. And then as soon as we hit the running state, it closes. And then as soon as that differential pressure exceeds 500, it opens again, and below 500, it closes. So there's an example of valve control using a virtual channel, and also permissives using a virtual channel. The last thing I want to cover is how we can create custom Modbus registers. And so to do that, I'm going to be using a Modbus tool that we use internally. And if I pull the Modbus registers on the DE4000, for example, you can see it register 40,090, the value of terminal 1, input 1, which is our suction pressure, 117. And in 40,091, you can see our discharge pressure at 399. But what we don't have available over Modbus is this new differential pressure virtual channel that we've created. So I know from the Modbus mapping that registers 40,300 and up are open. So what I'm going to do is I'm going to create a new Modbus register at 40,300. So to do that, I go to global, and I go to my Modbus script, and I say DP equals, you should always set your variables local when they're in a function, so that if you use the same variable name in another function, it won't spill over into that other function. Because if you don't declare them local, then they're global, and anytime you use that variable in any script, it'll have that same value. So I'm going to say local diff equals svert differential pressure. And again, I want to use (0) so we get a default value if it's not been created yet. And then we just use the set Modbus function, and we say set Modbus, and then the register we want to use, which would be 300, the value that we want to set that to, which would be the diff, and then the register block. So if we want to set that as a 40,000 register, so if we want it to be 40,300, then we just use a block number of 4. So that basically tells it to set it in the 40,000 register block as 40,300. And so I'm going to save that Modbus script. I'm going to go back to my Modbus tool. Oops. And I'm going to change this to start reading at 40,300. I'm just going to read 2 registers. I tell it to pull that. I'm now reading that differential pressure as 282 on that register 40,300. The other thing we can do with the Modbus script is we can set a floating point value. So to do that, so integer values, normal Modbus values are normally set as a 16-bit register. But if we use 2 16-bit registers in a row, we can store a 32-bit floating point value. So if we say set Modbus 32, it's actually going to set this value at register 300 and register 301. And we're going to use the same value diff, and we still want that in the 40,000 block. But this is going to actually write to 2 registers. So I'm going to save that. And if I go back to my Modbus tool, I'm now getting 2 16-bit values in 40,300 and 40,301. They don't really make any sense or match the value of our differential pressure when we look at them individually. But if I set the encoding type to 32-bit floating point and apply that and then read the values, you can see it's now coming out as 282.7. So it's taken that floating point value of our differential pressure and saved that into 2 Modbus registers as a floating point value. So I know we've covered kind of the whole gamut from the very basic Lua all the way up to custom Modbus scripting and valve control and permissives. So I hope that that's been informative. And do we have any questions on any of that?
It's an outstanding review, Bryan. Folks, any questions for Bryan on scripting and or anything related to D4000 configuration? Questions for Bryan?
And you might want to give Tim a minute. I don't know if he had anything planned, but just in case he did.
Tim,
Hey,
anything
Bryan.
from your side, sir?
Hey, Bryan, it is Shirali. Bryan, could you hear me?
Yes, I can hear you. Go ahead.
Okay. For me, just I want to be, the PIDs should be off until the run status. Can we do that one?
We're talking about Modbus here?
No, through the scripting.
Okay.
We want to, the PID, all the PID should be off until the run status. Once it is come to the run mode, then only we need to activate that PID mode. Can we do that?
Yes, we can set an override on the PID. Don't know that I have that script available right in front of me. Tell you what I'm going to do. I'm going to put my got my email address, brian.worth@horbiger.com.
I will send a PM. That is the best way. Okay.
Yeah, send me a message and I will look that up and get that code. But yes, we have complete control to turn PIDs on and off with scripting. We can basically override the PID and force the output value And then when we get to and that can be done, for example, in these outputs. So you could have something like, and this may not be the exact script. So this is just to show you what it may look like. It's going to be something like set svert PID 1 override comma 0. And that would set the PID output to 0, or you could set it to 100. Basically, it's percentage 0% to 100%. And you would set that in an earlier state, and then when you want to activate it, it's something like PID override -1, and the -1 tells it to turn off the override and go back to normal operation. But that's not the exact script, but it's something similar to that. But if you send me a message, I'll reply with the correct script for that.
Right. All right. Okay, thanks.